Hello. Welcome. It's good that you're here, settling in wherever you are. Perhaps the day has been long, or perhaps you're simply ready to let your thoughts slow down and drift towards something softer. Either way, you're welcome to stay as long as you like. There's no need to do anything but listen, or even half listen, as your mind begins to wander toward rest. Tonight, we're going to explore something very old and very gentle. We're going to follow the quiet story of ancient rivers, those slow currents that carve their way through stone and time, carrying water and sediment across landscapes that no longer exist. Rivers that flowed long before there were words to name them. Rivers that shaped continents with nothing but patience and persistence. You don't need to remember everything. You don't need to remember anything at all, really. This is just a soft place to let your thoughts settle, a calm voice moving through ideas that ask nothing of you. If you'd like to follow along for more stories like this one, you're welcome to, but there's no pressure, only an open invitation, as gentle as the topic itself. So let's begin. Let's step back, far back, into deep time, and let the ancient rivers show us their secrets. Rivers are among the oldest sculptors of the earth. Long before humans walked along their banks, long before forests grew thick with roots and leaves, rivers were already at work. They began as simple flows of water, tracing the lowest paths across barren rock, following gravity with a kind of blind devotion. There was no urgency in this, just water, moving downhill the way water always does. The very first rivers on Earth likely formed more than 4 billion years ago, not long after the planet's surface cooled enough to hold liquid water. Back then, the atmosphere was different, the sky a strange color, and the land was raw and lifeless. But even in that alien world, water found its way. It pooled in low places, overflowed, and began to carve the first channels. These rivers had no fish, no plants along their edges, no birdsong at dawn, just the quiet whisper of water over stone. And that whisper was enough. Over millions of years, those early rivers began to shape the landscape. They wore away at rock, grain by grain, carrying sediment downstream. The particles they moved were tiny, almost invisible, but they added up. A river doesn't need to hurry. It has all the time in the world. Some of the oldest evidence of ancient rivers comes from rocks more than 3 billion years old. Geologists have found sedimentary layers, smooth and rounded pebbles, patterns that could only have been shaped by flowing water. These rocks are like whispers from an unimaginably distant past, telling us that rivers were there, patient and persistent, even when the earth was young and strange. Rivers don't just move water. They move entire landscapes, slowly, steadily, without ever stopping. Every river carries sediment, tiny fragments of the mountains and hills upstream. Sand, silt, clay, pebbles. All of it travels downstream, suspended in the current or rolling along the riverbed. This process is called sediment transport, and it's one of the most calming forces in nature. There's no violence in it, just the gentle, endless work of moving the world piece by piece. The amount of sediment a river carries depends on many things. The speed of the current, the type of rock upstream, the slope of the land. Fast rivers carry more, including larger particles. Slow rivers carry mostly fine silt and clay. Particles so small they make the water look cloudy and soft. But whether fast or slow, every river is a conveyor belt, moving the land from high places to low places, from mountains to the sea. And this movement is ancient. The sediment in a riverbed might have started its journey thousands of years ago, or even longer. A grain of sand might have been part of a mountain peak, then broken free, tumbled down a slope, and entered stream. From there, it traveled through countless bends and pools, resting for decades in a quiet eddy before moving on. Eventually, it reached the main river, joined millions of other grains, and continue the long journey toward the ocean. There's something deeply restful in that image. The idea that even a single grain of sand has a story, a slow and winding journey that took longer than any human lifetime. Rivers are patient storytellers, and every particle they carry is a word in a story that began long ago and will continue long after we're gone. One of the most beautiful things rivers do is meander. If you've ever looked at a river from above, you've probably noticed that it rarely flows in a straight line. Instead, it curves and loops, bending back on itself in smooth, graceful arcs. These curves are called meanders, and they form naturally, almost inevitably, as a river flows across flat or gently sloping land. Meanders form because water doesn't flow evenly across a riverbed. Even a tiny irregularity, a small bump or dip, can change the way water moves. Water flowing faster on one side of the channel begins to erode the bank there, while slower water on the other side deposits sediment. Over time, this creates a curve, and once a curve begins, it tends to grow. The river swings wider and wider, carving a loop that can eventually become so extreme that the river cuts through its own banks and creates a new, straighter path. The old loop is left behind, forming what's called an oxbow lake, a quiet crescent of water that slowly fills with sediment and vegetation. This process takes time, decades, centuries, even millennia, but the river doesn't mind. It keeps flowing, keeps curving, keeps reshaping the land with a kind of serene inevitability. There's no plan, no intention, just water, following the path of least resistance, creating beauty as a side effect. Meanders are not just beautiful, they're also incredibly efficient. By lengthening the river's path, they reduce the slope and slow the current, which reduces erosion and allows the river to carry sediment more gently. In a way, a meandering river is a river at peace with itself, flowing in a rhythm that balances movement and stillness. Some ancient rivers created meanders so large they can still be seen today, even though the rivers themselves have long since vanished. Satellite images and geological surveys have revealed the ghostly outlines of river channels that flowed millions of years ago, their curves still visible in the landscape, like echoes of water that once moved there. These ancient meanders are called palaeochannels, and they tell us where rivers used to flow, what the climate was like, and how the land has changed over deep time. In the Sahara Desert, for example, scientists have found evidence of vast river systems that flowed across the region thousands of years ago, when the climate was wetter and the desert was green. Radar images reveal buried channels, wide and winding, hidden beneath the sand. These rivers are gone now, but their shapes remain, preserved in the rock and soil, waiting quietly to be discovered. Rivers also build. While they're busy eroding the land in some places, they're depositing sediment in others. And one of the most remarkable things they build is a delta. A delta forms where a river meets a body of still water, usually the ocean or a large lake. When the river slows down, it can no longer carry all its sediment, so it drops it, layer by layer, building up land to the river's mouth. Deltas are some of the most fertile and dynamic landscapes on Earth. They're constantly changing, growing, shifting, as the river deposits new sediment and the ocean pushes back with tides and waves. The result is a complex, ever-changing mosaic of channels, islands, wetlands, and mudflats. Deltas are places where land and water meet and mingle, where the boundary between them is soft and uncertain. Some ancient deltas have been preserved in the rock record, turned to stone over millions of years. Geologists can read these rocks like pages in a book, tracing the paths of rivers that flowed long ago, mapping the coastlines of ancient seas. The rocks tell stories of floods and droughts, of rivers that shifted course, of deltas that grew and shrank with the changing climate. The Mississippi River Delta, for example, has been building for thousands of years, but its shape has changed many times. The river has switched course repeatedly, abandoning old channels and carving new ones, leaving behind a complex pattern of old delta lobes that can still be seen in maps and satellite images. Each lobe represents a different chapter in the river's history, a different path it took to the sea. And this process is ongoing. Even now, the Mississippi is depositing sediment, building new land, though human interference has complicated the process. But the river's instinct, if we can call it that, is still the same, to carry sediment downstream and lay it gently at the journey's end. Rivers have been shaping the earth for billions of years, but they haven't always looked the same. In the distant past, before plants colonized the land, rivers behaved very differently. Without roots to hold the soil in place, riverbanks were unstable and easily eroded. Rivers were wider, shallower, and braided, splitting into multiple channels that shifted constantly. The landscape was raw and open, and rivers wandered freely across it. Then, Around 400 million years ago, plants began to spread across the land. First mosses and liverworts, then ferns and early trees. Their roots stabilized the soil, and for the first time, rivers could carve deep, narrow channels with stable banks. This changed everything. Rivers became more sinuous, more meandering, more like the rivers we know today. The arrival of plants didn't just change the land, it changed the rivers too. This shift is visible in the rock record. Sedimentary rocks older than the arrival of land plants show broad, braided river systems. Younger rocks show narrow, meandering channels. It's a quiet revolution, written in stone, a reminder that rivers and life have always been connected, shaping each other in ways both subtle and profound. Ancient rivers also carried something else: life. Once life moved onto the land, rivers became corridors, pathways for plants and animals to spread and migrate. Fish evolved in ancient rivers and lakes, adapting to the currents and the changing chemistry of the water. Amphibians crawled out of rivers onto muddy banks, beginning the long evolutionary journey that would eventually lead to reptiles, birds, and mammals. Fossils found in ancient river sediments give us glimpses of these early ecosystems. Fossilized fish, shells, plant fragments, even footprints preserved in mud that hardened into stone. These fossils tell us that rivers were not just channels of water. They were channels of life, connecting different parts of the landscape, allowing species to move and evolve. Some of the most famous fossils in the world come from ancient river deposits. The dinosaur fossils of the American West, for example, are often found in rocks that were once riverbeds or floodplains. The animals died near the water, their bodies were buried in sediment, and over millions of years, they turned to stone. The rivers that buried them are long gone, but the fossils remain, silent witnesses to a world that no longer exists. Rivers also record the climate, the size and shape of a river channel, the type of sediment it carries, the patterns of erosion and deposition. All of these things are influenced by the climate. A river in a wet, rainy region behaves differently from a river in a dry region. By studying ancient river deposits, scientists can reconstruct what the climate was like millions of years ago. For example, thick layers of coarse gravel suggest a river with a strong, fast current, which usually means a wet climate with heavy rainfall. Thin layers of fine silt suggest a slower, gentler river, which might indicate a drier climate or a flatter landscape. Cross-bedding, the angled layers you sometimes see in sedimentary rock, can tell you which way the river was flowing and how fast. In this way, ancient rivers become archives of Earth's climate history. They don't speak in words, but in textures and patterns, in the arrangement of sand and stone. And if you know how to read them, they can tell you stories about monsoons that drenched ancient continents, droughts that lasted for centuries, ice ages that locked up water and changed the flow of rivers around the world. One of the most calming facts about rivers is that they follow the simplest possible rule: water flows downhill. That's it. No matter how complex a river system becomes, no matter how many tributaries and branches and meanders it develops, it all comes down to that one simple principle. Water seeks the lowest point, and it will find a way to get there, even if it takes millions of years. This simplicity is part of what makes rivers so soothing to think about. They're not trying to do anything. They're not striving or struggling. They're just following the path that gravity offers them, moving with a kind of effortless inevitability. There's a lesson in that, perhaps, a reminder that some of the most powerful forces in nature are also the most patient and unhurried. And yet, within that simplicity, rivers create extraordinary complexity. Every bend, every pool, every riffle and rapid is the result of countless small interactions between water, sediment, and rock. The river is constantly adjusting, constantly finding a new balance, responding to changes in the landscape and the climate. It's a dynamic system, always in motion, but never in a hurry. Rivers also connect. They gather water from vast areas, collecting rainfall and snowmelt from every hill and valley in their drainage basin. All of that water flows together, merging in streams and tributaries, eventually joining the main river and flowing toward the sea. In this way, a river is like a tree in reverse, with branches spreading out across the landscape, gathering water and funneling it into a single trunk. This network of streams and rivers is called a drainage system, and it's one of the most elegant patterns in nature. From above, it looks almost fractal, with smaller streams feeding into larger ones, which feed into larger ones still, all the way down to the ocean. The pattern repeats at every scale, from tiny rivulets no wider than your hand to rivers so large they can be seen from space. And this pattern is ancient. Drainage systems form naturally, almost inevitably, whenever water falls on land. They've been forming for as long as there's been rain, for as long as there's been land to flow across. Some of the drainage patterns we see today are millions of years old, shaped by rivers that have been flowing in the same general direction for longer than our species has existed. There's something deeply comforting in that continuity. The idea that the same rivers, or their descendants, have been flowing for so long, through so many changes, so many rises and falls of mountains and seas. Rivers are patient. They outlast almost everything. Ancient rivers also carried minerals. As water flows over rock, it slowly dissolves certain minerals, carrying them away in solution. This process is called chemical weathering, and it's one of the ways rivers shape the chemistry of the ocean. Over millions of years, rivers have delivered vast quantities of dissolved minerals to the sea, including calcium, sodium, magnesium, and silica. These minerals are what makes seawater salty, and they're essential for many forms of marine life. But rivers don't just take from the land, they also give. The sediment they carry is rich in nutrients, and when it's deposited on floodplains or in deltas, it creates some of the most fertile soil on Earth. Ancient civilizations knew this. The Egyptians built their society around the Nile, relying on its annual floods to replenish the soil. The Mesopotamians did the same with the Tigris and Euphrates. Rivers were not just sources of water, they were sources of life. Even today, many of the world's most productive agricultural regions are located on river floodplains or ancient river terraces. The soil there is deep and rich, built up over thousands of years by the patient work of rivers depositing sediment, layer by layer. It's a gift from the past, from rivers that flowed long before anyone was there to see them. Rivers also create their own ecosystems. The water itself is a habitat, home to fish, insects, crustaceans, and countless microorganisms. The banks and floodplains support plants, which in turn support animals. And the river connects all of these habitats, allowing nutrients and organisms to move and spread. In ancient times, before humans altered so many rivers, these ecosystems were incredibly rich and diverse. Rivers teemed with life, from the smallest algae to the largest fish. Floodplains were vast wetlands, full of birds and amphibians, and all of it was connected by the flow of the river, the endless movement of water from the mountains to the sea. Some of that richness is still visible in rivers that have been less affected by human activity. In the Amazon, for example, the river and its tributaries support thousands of species of fish, many of them found nowhere else. The river's annual flood cycle creates a dynamic, ever-changing landscape of forests, wetlands, and channels, each with its own unique community of life. And this richness is ancient. The Amazon River system has been evolving for millions of years, and the species that live there have co-evolved with the river, adapting to its rhythms and its changes. The river is not just a body of water. It's a living, breathing ecosystem, shaped by time and flow. Rivers also have a sound. If you've ever sat by a river, you know this. The sound of water moving over rocks, the gentle rush and gurgle, the way it changes depending on the depth and speed of the current. It's one of the most universally calming sounds in nature, and there's a reason for that. Our ancestors lived near rivers, relied on them, listened to them every day. That sound is wired into us, a signal of safety and abundance. Ancient rivers made the same sounds. The physics of flowing water hasn't changed. A river 300 million years ago sounded much like a river today. The same soft rush, the same murmur. And if you could somehow travel back in time and sit by one of those ancient rivers, you'd hear something familiar, something comforting, even in a world that would otherwise seem utterly alien. There's a kind of poetry in that. The idea that some things are constant, that the sound of water over stone is the same now as it was in the deep past, and will be the same in the deep future. Rivers are anchors in time, connecting us to the Earth's long history. Rivers also freeze, and when they do, they change completely. In cold climates, rivers can freeze solid in winter, their surfaces covered with thick ice. But beneath the ice, water often continues to flow, moving slowly through the dark. When spring comes, the ice breaks up and the river returns to life, its flow quickening as snow melt swells the current. Ancient rivers experienced this too, especially during ice ages, when glaciers covered much of the northern hemisphere. Rivers that flowed near the ice were fed by meltwater, and they carried vast amounts of sediment, ground up by the glaciers and flushed downstream. These glacial rivers were powerful and fast, carving deep valleys and depositing thick layers of gravel and sand. Some of the landscapes we see today were shaped by these glacial rivers. The channeled scablands of Washington State, for example, were carved by catastrophic floods from a glacial lake that burst through its ice dam repeatedly during the last ice age. The floods were unimaginably large, carrying more water than all the rivers on Earth combined, and they scoured the land down to bedrock, creating a landscape of channels, cliffs, and waterfalls that still looks raw and dramatic today. But even these violent events were part of the river's story. The floods came and went, the ice advanced and retreated, and the rivers adjusted, finding new paths, new rhythms. They endured, as rivers always do. Rivers also disappear. Sometimes a river dries up, its water diverted, or its source exhausted. Sometimes it's buried under sediment or lava. Sometimes it simply changes course, abandoning its old channel and carving a new one. And when a river disappears, it leaves behind a kind of ghost, a trace of where it used to be. These traces can last for millions of years. Dry riverbeds, filled with sediment, can be preserved in the rock record. Ancient channels, now buried deep underground, can be detected with geophysical surveys. Even on other planets, scientists have found evidence of ancient rivers, long dry channels carved into the surface of Mars, hinting at a time when water flowed there, under a thicker atmosphere, in a warmer climate. These ghost rivers are reminders of impermanence, of the way landscapes change and evolve. But they're also reminders of persistence. Even when a river is gone, its mark remains, written into the land, waiting to be read by anyone who knows how to look. Rivers also carry stories, not just geological stories, but human stories. For as long as there have been people, there have been rivers, and people have lived beside them, depended on them, told stories about them. Rivers are places of meeting and parting, of trade and travel, of life and death. They're woven into our mythology, our history, our sense of place. Ancient rivers witnessed the rise and fall of civilizations. They saw the first farmers plant their crops, the first cities rise on their banks, the first boats set out to explore the world. They carried goods and people, ideas and diseases. They were highways and barriers, sources of wealth and sources of conflict. And through it all, the rivers kept flowing. Empires rose and fell, cities were built and abandoned, but the rivers endured, patient and indifferent, following the same paths they'd followed for millennia. There's something humbling in that, a reminder that we are temporary, but the rivers are not. Some ancient rivers have names that echo through history. The Nile, the Tigris, the Euphrates, the Indus, the Yellow River. These rivers were the cradles of civilization, the places where human society first took root and flourished. They provided water for drinking and irrigation, fish for food, reeds for building, clay for pottery. They made settled life possible, and they're still there, still flowing, though much changed by human activity. Dams and diversions, pollution and overuse have altered them profoundly. But the rivers themselves, the water and the flow, the patient work of carrying sediment to the sea, that continues. The rivers remember what they've always been, even if we sometimes forget. The ancient rivers carried more than water and sediment. They carried dissolved minerals, trace elements pulled quietly from the rocks they touched. Each river developed its own chemical signature, a unique blend of calcium, magnesium, silica, and iron that reflected the geology of its watershed. These dissolved substances traveled invisibly, molecule by molecule, changing the character of the water as it flowed. The chemistry was never static, shifting with seasons, with rainfall, with the slow weathering of stone upstream. And in this patient dissolution, rivers became sculptors not just of land, but of the very composition of the ocean. The Amazon River, one of Earth's most ancient drainage systems, pours more than 200,000 cubic meters of water into the Atlantic every single second. This immense flow carries with it a chemical load so vast it changes the salinity and color of the ocean for hundreds of kilometers offshore. The dissolved minerals, the organic compounds, the microscopic particles, all of this material represents millions of years of patient erosion, the breaking down of mountains grain by grain. The Amazon basin itself is ancient beyond easy comprehension, its roots stretching back more than 100 million years, its course shifting and reforming as continents drifted and climates changed. Rivers remember ice ages in their valleys. When glaciers advanced during the Pleistocene, many rivers were buried, diverted, or completely rearranged. The meltwater from retreating ice sheets carved new channels, deepened old ones, and left behind landscapes of terraces and abandoned meanders. These glacial rivers carried enormous volumes of sediment, grinding rock into fine flour that turned the water milky white. Today, you can still see this glacial flour in rivers fed by mountain glaciers. The Ganges, the Indus, rivers flowing from the Himalayas still carry the signature of ice, still transport the evidence of ancient cold. The sediment settles in layers, preserving a record of each glacial pulse, each warming period, each shift in Earth's climate. Some ancient rivers flowed in directions opposite to their modern courses. The Congo River, for instance, once drained toward the interior of Africa, feeding vast inland lakes. Tectonic shifts gradually tilted the land, and the river reversed, carving its way toward the Atlantic. This reversal left behind a landscape of puzzles, dry valleys pointing the wrong way, lakes with no apparent outlets, sediment layers that tell stories of water flowing uphill, or rather, flowing in directions that no longer make sense. These reversals remind us that rivers are not permanent features, but temporary paths that water finds across a restless, shifting planet. The Nile, often called the world's longest river, has flowed northward for millions of years, but its character has changed dramatically. During wetter periods in Africa's past, the Nile carried far more water, cutting deeper into its valley, spreading wider across its floodplain. During drier periods, it shrank, leaving terraces high above the current channel. These terraces are like rings in a tree, marking the river's history, recording the rise and fall of rainfall across an entire continent. Archaeologists study these terraces to understand when humans could have crossed the river, when floodplains were fertile, when droughts drove populations away. The river's memory is written in stone and soil, patient and legible. Rivers also shape the evolution of fish in ways both subtle and profound. Isolated river systems became laboratories of speciation, where populations of fish diverged into new forms, adapted to local conditions, developed unique behaviors. The ancient rivers of the Amazon basin, for instance, harbor more species of freshwater fish than any other river system on Earth. Perhaps 3,000 species, many still undescribed by science. Each tributary, each isolated pool, each stretch of rapids created barriers and opportunities, driving evolution in countless directions. The fish carry the history of the river in their genes, a living archive of ancient connections and separations. The sediment that rivers carry is not uniform. It sorts itself by size and weight as it travels. Larger pebbles and cobbles settle out first in the fast-moving upper reaches. Sand travels farther, accumulating in the middle sections and along riverbanks. The finest clay particles stay suspended longest, sometimes traveling thousands of kilometers before finally settling in the quiet waters of a delta or the open ocean. This sorting process creates distinct layers in the geological record, each grain size telling a story about the energy of the water that carried it. Geologists read these layers like pages in a book, inferring ancient river speeds, flood events, seasonal changes, all from the patient arrangement of particles. Some rivers carry so much sediment that they build land faster than the ocean can erode it. The Mississippi River, over the past 7,000 years, has extended Louisiana's coastline far into the Gulf of Mexico, depositing layer upon layer of mud and silt. The river switches its course every 1,000 years or so, abandoning old channels and carving new ones, distributing sediment across a vast delta plain. Each abandoned channel becomes a quiet bayou, a still waterway where sediment settles and plants take root. The delta is a living, shifting landscape built entirely from material carried down from the continent's interior, from the Rocky Mountains, the Great Plains, the Appalachian foothills, a gathering of the continent, delivered grain by grain to the sea. Ancient rivers also transported volcanic ash, spreading it across continents. When a volcano erupted, ash fell into rivers, and the water carried it downstream, sometimes for thousands of kilometers. These ash layers, preserved in sedimentary rock, serve as time markers for geologists. Because volcanic eruptions are geologically instantaneous events, an ash layer represents a single moment in time, a horizon that can be traced across vast distances. By dating the ash, scientists can correlate rock layers from different regions, reconstructing the geography of ancient river systems, understanding how water flowed across landscapes that no longer exist. The speed of a river varies not just along its length, but also across its width and depth. Water near the banks and the bottom moves more slowly, slowed by friction with rock and soil. Water in the center, near the surface, moves fastest, flowing smoothly and swiftly. This variation in speed creates complex patterns of erosion and deposition. The fastest water carves the deepest channels. The slowest water drops its sediment. Over time, these patterns shape the river's cross-section, creating a profile that balances the water's energy with the resistance of the landscape. It is a dynamic equilibrium, constantly adjusting, never quite still. Rivers also carry sound. The movement of water over rocks, the tumbling of pebbles, the hiss of sand grains sliding past each other. All of this creates a continuous, low-frequency rumble. In ancient times, long before human ears existed to hear it, rivers filled the world with this patient noise, a soundtrack of erosion, a hymn to the persistence of water. Even today, if you sit beside a river and listen carefully, you can hear the work being done, the quiet grinding of stone, the whisper of sediment in motion. It is a sound that has not changed in millions of years, a constant presence in the history of the planet. Some ancient rivers left behind only their ghosts. Dry valleys where water once flowed, now silent and empty. The deserts of North Africa, the Middle East, and Central Asia are crossed by these fossil rivers, channels carved during wetter periods thousands of years ago. Satellite images reveal their courses, winding across landscapes where rain rarely falls today. These dry rivers still shape the land, channeling rare floods, guiding the movement of sand dunes, influencing where plants can grow. They remind us that climate is not constant, that rivers come and go, that the Earth's surface is always in conversation with the sky. The water in a river is never the same water twice. Each molecule flows downstream, joins the ocean, evaporates, falls as rain, and begins the journey again. This cycle has continued for billions of years. The same water, endlessly recycled, endlessly renewed. The water that flowed in ancient rivers is the same water that flows today, the same water that fills your glass, the same water that makes up most of your body. We are connected to ancient rivers not metaphorically, but literally, through the patient circulation of water across the planet. It is a cycle without beginning or end, a loop of transformation and return. Rivers also create microclimates along their banks. The presence of water moderates temperature, increases humidity, supports lush vegetation even in otherwise dry regions. These riparian zones are ribbons of life, corridors of green threading through varied landscapes. In ancient times, these corridors served as highways for the movement of animals and plants, allowing species to spread across continents, to survive climate shifts, to find refuge during hard times. The rivers were not just waterways, but lifelines, connecting ecosystems, enabling the flow of life as surely as they enabled the flow of water. The gradient of a river, the steepness of its descent, determines much about its character. A steep gradient means fast water, high energy, vigorous erosion. A gentle gradient means slow water, low energy, extensive deposition. Ancient rivers with steep gradients carve narrow, deep valleys, transporting coarse sediment, creating rocky beds. Ancient rivers with gentle gradients meandered widely, deposited fine sediment, built broad floodplains. By studying the sediment and the shape of ancient river valleys, geologists can calculate the gradient, and from that, infer the topography of landscapes that have long since eroded away. The river becomes a key to reconstructing vanished worlds. Some rivers flow underground for part of their course, disappearing into limestone caves, traveling through darkness, then re-emerging into daylight kilometers away. These underground rivers carve vast cave systems, dissolving rock slowly, creating chambers and passages that can persist for millions of years. The water in these caves is often incredibly clear, filtered by its passage through rock, stripped of sediment, moving quietly through stone. Ancient underground rivers left behind dry caves, some of which preserve fossils, ancient human artifacts, even footprints pressed into soft mud and hardened over millennia. These caves are time capsules, sealed away from the surface world, preserving moments from the deep past. The energy of a river is immense, even when it appears calm. The slow, steady flow of a large river carries more energy than a raging mountain stream, simply because of the volume of water in motion. This energy does work, lifting sediment, carving rock, shaping landscapes. Over geological time, the cumulative work of a river can level mountains, fill ocean basins, alter the course of evolution. And yet, the river does this work without haste, without violence, simply by flowing day after day, year after year, millennium after millennium. It is patient power, quiet and inexorable. Rivers also influence the weather. Large rivers release moisture into the atmosphere through evaporation, contributing to local and regional rainfall. The Amazon River and its tributaries, for instance, recycle water so effectively that much of the rain falling in the western Amazon originally fell in the eastern Amazon, then flowed toward the Andes, evaporated, and fell again. This recycling creates a stable, wet climate that supports the rainforest, which in turn supports the river. It is a feedback loop, a partnership between water and life, sustained over millions of years. The river and the forest are not separate entities, but parts of a single, integrated system. Ancient rivers sometimes flowed across landscapes that are now deep underwater. During ice ages, when sea levels dropped, rivers extended their courses across exposed continental shelves, carving valleys that are now submerged. The Hudson River, for instance, once flowed across what is now the floor of the Atlantic, cutting a deep canyon that still exists, hidden beneath the waves. These drowned river valleys, called submarine canyons, channel sediment from the continental shelf into the deep ocean, continuing the river's work even after the river itself has been swallowed by the sea. The past is not always visible, but it persists, shaping the present in hidden ways. The color of a river tells a story. Clear water means little sediment, often indicating a river flowing over hard, resistant rock, or a river draining a landscape with dense vegetation that holds soil in place. Brown or tan water means high sediment load, often from erosion in areas with sparse vegetation or soft, easily weathered rock. Green water can indicate high levels of algae, often a sign of nutrient enrichment. Black or tea-colored water, common in tropical rivers, comes from dissolved organic matter, tannins leached from decaying plants. Each color is a clue, a window into the river's watershed, the geology, the biology, the chemistry of the land it drains. Rivers also create natural levees along their banks. During floods, when the river overflows its channel, the water slows as it spreads across the floodplain. The slowdown causes sediment to drop out of suspension, and the coarsest sediment settles first, right at the edge of the channel. Over many floods, this sediment builds up, forming raised ridges along the riverbanks. These natural levees can grow high enough to contain the river during normal flows, creating a channel that sits higher than the surrounding floodplain. Ancient rivers built levees that still shape modern landscapes, guiding water, influencing where people build, determining the pattern of fields and settlements. Some ancient rivers carried gold. As water eroded, gold-bearing rock, tiny flakes and nuggets of gold, being heavy, settled quickly in the riverbed, accumulating in places where the current slowed, behind boulders, in cracks, on the inside of meanders. These placer deposits have been mined by humans for thousands of years, but the rivers have been concentrating gold for millions of years, patiently sorting it from worthless rock, gathering it grain by grain. The gold in a river is ancient, often billions of years old, freed from deep rocks, carried by water, waiting to be found. Rivers also respond to the seasons, swelling with snowmelt or monsoon rains, shrinking during dry periods. This seasonal rhythm has remained consistent for millions of years, a predictable pulse that life has adapted to. Fish time their migrations to high water. Plants along riverbanks have evolved to tolerate periodic flooding. Birds nest when water levels are right for feeding. The river is a clock, marking time not in hours or days, but in the rise and fall of water, the coming and going of floods, the patient cycle of wet and dry. The oldest rivers on Earth are difficult to identify with certainty because rivers change course, and the rocks they deposit can be reworked by later rivers. But some river systems have likely existed, in some form, for hundreds of millions of years. The Finca River in Australia, for instance, may have been flowing for over 300 million years, making it one of the oldest rivers still following a recognizable course. It has witnessed the rise and fall of mountain ranges, the drift of continents, the evolution of countless species. To stand beside such a river is to touch deep time, to feel the weight of ages in the quiet flow of water. Rivers also create oxbow lakes, those crescent-shaped bodies of water that are floodplains. When a meandering river cuts through the neck of a meander, it shortens its course, leaving the old loop isolated. The abandoned channel fills with water, becomes a lake, gradually silts up, and eventually becomes a marsh, then dry land. This process can happen over decades or centuries, a quick transformation by geological standards. Ancient floodplains are littered with the ghosts of oxbow lakes, visible as curved depressions, subtle changes in soil, patterns in vegetation. Each one marks a moment when the river chose a new path, a small decision in the river's long, wandering journey. The sediment in a river is not just rock. It includes organic matter, the remains of plants and animals, pollen grains, seeds, fragments of wood. This organic material is a record of the ecosystems the river drains, a snapshot of the life upstream. When this material is buried and preserved, it becomes part of the geological record, allowing scientists to reconstruct ancient environments, to understand what plants grew along the riverbanks, what animals lived in the watershed, how ecosystems changed over time. The river is an archivist, gathering evidence, transporting it downstream, depositing it in layers that future generations can read. Rivers also shape human language and culture. Many of the world's oldest place names are river names, words passed down through generations, sometimes for thousands of years. The names often describe the river's character, its color, its speed, its size, the life it supports. These names are a form of memory, a way of holding on to knowledge about the landscape, about the river's behavior, about its importance to survival. In this way, rivers have shaped not just the physical world, but the human world, influencing how we think, how we speak, how we understand our place in the landscape. Some rivers flow through multiple climate zones, beginning in snowy mountains and ending in tropical lowlands, or starting in rainforests and flowing through deserts. These rivers carry water from one world to another, connecting ecosystems that would otherwise be isolated. The Nile, for instance, brings water from the rainy highlands of Ethiopia and East Africa through the Sahara Desert, creating a ribbon of life in one of the driest places on Earth. This connection has persisted for millions of years, a lifeline across a harsh landscape, a reminder that water flows according to gravity, not climate, and in doing so, creates unexpected oases, improbable gardens, places where life thrives against the odds. Rivers also carry heat. Water has a high heat capacity, meaning it can absorb and transport large amounts of thermal energy. A river flowing from a warm region into a cooler one brings warmth. A river fed by cold mountain streams brings coolness. This thermal transport influences local climates, moderates temperatures, affects the distribution of species. Ancient rivers carried heat across continents, subtly shaping climates, creating microclimates that persisted long enough for life to adapt, to specialize, to evolve in response to these stable, river-created conditions. The mouth of a river, where it meets the ocean, is a place of mixing and transformation. Fresh water meets salt water, sediment meets waves, river currents meet tidal currents. This mixing creates estuaries, some of the most productive ecosystems on Earth, rich in nutrients, teeming with life. Ancient river mouths were similarly productive, supporting abundant fish, shellfish, birds, and the predators that fed on them. Fossil beds near ancient river mouths often contain a remarkable diversity of species, evidence of the richness these environments supported. The estuary is neither river nor ocean, but something in between, a zone of transition, a place where boundaries blur and life flourishes. Rivers also carry pollen, those tiny grains that plants produce for reproduction. Pollen is remarkably durable, and when it settles in river sediment, it can be preserved for millions of years. By extracting and identifying fossil pollen from ancient river deposits, scientists can reconstruct the vegetation of past landscapes, understanding what trees grew, what flowers bloomed, how plant communities changed over time. This technique, called palaeochannels, allows us to see ancient worlds not just as bare geology, but as living landscapes, green and flowering, buzzing with insects, shaded by forests that have long since vanished. Some ancient rivers were enormous by modern standards. During the Cretaceous period, when the climate was warmer and sea levels were higher, rivers drained vast, low-lying continents, carrying immense volumes of water and sediment. The Western Interior Seaway, which split North America in two, was fed by rivers from both the west and the east, rivers that built deltas, deposited sediment, and created the rock formations that now form the Great Plains. These rivers are gone, but their work remains, visible in the layers of sandstone and shale that stretch across the continent, a testament to the power of water to shape worlds. Rivers also create natural bridges, arches, and tunnels. When a river undercuts a rock layer, it can create an overhang that eventually collapses, leaving behind a natural bridge or arch. These features are rare and fragile, often lasting only a few thousand years before erosion brings them down. But in the long history of rivers, countless such features have formed and fallen, each one a brief sculpture, a momentary collaboration between water and stone. The rivers care nothing for beauty, yet they create it accidentally, inevitably, as a byproduct of their patient work. The temperature of river water varies with depth, season, and source. Cold mountain streams, fed by snowmelt, remain chilly even in summer. Lowland rivers in tropical regions can be as warm as bathwater. These temperature differences affect everything: the amount of dissolved oxygen, the types of organisms that can survive, the rate of chemical reactions, the speed of decomposition. Ancient rivers had the same temperature variations, and life adapted accordingly, with cold water species in the highlands, warm water species in the lowlands, and a gradient of adaptation in between. Temperature is a quiet force, shaping life as surely as the flow of water itself. Rivers also carry sound in another way, the sound of human history. The songs sung by people working along rivers, the stories told about river spirits and river gods, the names given to rapids and pools and bends. These sounds are not preserved in rock, but they are part of the river's history nonetheless, part of the long conversation between water and the creatures that depend on it. Ancient peoples knew their rivers intimately, understood their moods, their dangers, their gifts. That knowledge, passed down through generations, is a form of memory as real as the sediment layers, as enduring as the stone. Some rivers disappear entirely, not into the ocean, but into the ground or into desert sands. These endorheic rivers drain into inland basins, where the water evaporates, leaving behind salt flats and dry lake beds. The ancient rivers that fed Lake Bonneville in North America, or the rivers that once filled the Darien Basin in Central Asia, followed this pattern, carrying water into basins with no outlet to the sea. These rivers were no less real, no less important than rivers that reach the ocean. They supported life, shaped landscapes, left behind sediment and fossils. They remind us that not all journeys end at the sea, that some paths lead inward to quiet endings in sun-baked basins under vast skies. Rivers also create jobs for microbes. Bacteria and archaea thrive in river sediments, breaking down organic matter, cycling nutrients, transforming chemicals. These microbes are ancient, their lineages stretching back billions of years, and they have been working in rivers for as long as rivers have existed. They are invisible, uncountable, yet essential. Without them, organic matter would accumulate, nutrients would be locked away, the river would choke on its own abundance. The microbes are the river's quiet partners, the unseen laborers that keep the system running, that close the loops, that ensure nothing is wasted. The flow of a river is fractal, meaning it exhibits similar patterns at different scales. The branching of tributaries resembles the branching of smaller streams, which resembles the branching of tiny rivulets. The turbulence in a rapid resembles the turbulence in a small eddy, which resembles the swirling of water around a single pebble. This self-similarity is a signature of natural processes, a hint that the same physical laws operate at all scales, that the river is a unified system, coherent from the smallest trickle to the mightiest flood. It is a kind of beauty that mathematics can describe, but that the river creates without thought, without intention, simply by flowing. The ancient rivers carried more than water and stone. They transported sound itself, a low-frequency hum that moved through their beds, a vibration that traveled faster through wet sediment than through air. Fish and amphibians felt these sounds as pressure waves against their lateral lines, reading the river's mood long before they could see a change in current. The sound of moving water created a constant background, a white noise that masked other frequencies, offering shelter to prey and predator alike. In the Devonian period, over 360 million years ago, these acoustic landscapes shaped how early vertebrates communicated, how they chose mates, how they warned of danger. The rivers were not silent corridors, but resonant chambers, each bend and pool creating its own acoustic signature, each rapid adding a higher pitch to the endless song. And within that song, there were pauses, moments when the river slowed so completely that it seemed to hold its breath. These still pools formed in the lee of large boulders, in the deep bends where current lost its grip, in the wide stretches where the river spread thin and lazy across flat land. Here, sediment settled in perfect horizontal layers, each grain finding its resting place according to size and weight. The finest clay particles drifted down last, taking hours or even days to complete their descent through the quiet water. These still zones became natural laboratories where chemical reactions proceeded without the disruption of turbulence, where minerals precipitated slowly into delicate crystals, where organic matter decomposed in predictable stages. Ancient still pools preserve some of the most detailed fossils ever found, capturing the outline of soft tissues, the impression of feathers, the shadow of skin that would have vanished in faster water. The temperature of ancient rivers varied, not just with season, but with depth and speed. Surface water warmed quickly under the sun, especially in shallow stretches where light penetrated to the bottom. But deeper channels held cooler water, denser and slower to respond to atmospheric changes. This thermal stratification created invisible layers within the river, boundaries where warm and cool water met, but did not immediately mix. Fish and other organisms learned to navigate these thermal zones, seeking comfort in the temperatures that suited their metabolism. Cold-blooded creatures could regulate their body temperature by moving up or down within the water column, finding the precise degree that optimized their digestion, their growth, their reproductive readiness. Ancient rivers were not uniform tubes of flow, but complex three-dimensional environments where every depth offered different conditions, different opportunities, different challenges. Some ancient rivers flowed through landscapes of extreme aridity, carrying water from distant mountains across hundreds of miles of desert. These rivers were lifelines in barren lands, their channels marked by ribbons of green vegetation that stood in stark contrast to the surrounding dunes and rock. The Nile in ancient times, long before human civilization, rose along its banks, flowed through the Sahara when that region was even drier than today, fed by monsoon rains that fell on the Ethiopian highlands. The river's annual flood was so reliable, so predictable, that it became a clock by which ecosystems set their rhythms. Plants timed their germination to the flood's arrival. Animals timed their migrations to the retreat of the waters. And the entire biological community synchronized itself to this one overwhelming fact of liquid abundance in a dry world. The chemistry of river water changed as it flowed, not just from the addition of tributaries, but from countless small interactions with the air above and the bed below. Oxygen dissolved into the water at the surface, especially in turbulent stretches where waves and spray increased the contact between liquid and atmosphere. This dissolved oxygen was essential for fish and invertebrates, and its concentration varied with temperature, with altitude, with the amount of organic matter decaying in the water. Ancient rivers in warm climates often had lower oxygen levels than cold rivers, because warm water holds less dissolved gas. During periods of Earth's history, when atmospheric oxygen was lower than today, rivers carried less of this vital element, and aquatic life adapted to survive in what we would consider oxygen-poor conditions. Some fish developed accessory breathing organs. Some invertebrates evolved hemoglobin-like compounds to capture oxygen more efficiently, and entire ecosystems restructured themselves around the challenge of scarcity. Ancient rivers also carried light, or rather, they filtered and transformed it. Clear water allowed sunlight to penetrate deeply, reaching the riverbed in shallow areas and supporting photosynthetic algae and aquatic plants. But most rivers were not perfectly clear. Suspended sediment scattered light, giving the water a milky or brownish appearance and reducing visibility to inches or feet. Dissolved organic compounds, tannins leached from decaying leaves and wood, stained some rivers the color of tea, a deep amber that absorbed blue wavelengths and let through the warmer reds and yellows. These tea-colored rivers were common in forested regions where organic matter was abundant, and they created a different visual world for their inhabitants, a perpetual twilight even in shallow water. The amount and quality of light shaped which organisms could thrive, which hunting strategies worked, which colors and patterns were visible to potential mates. The gradient of a river, the steepness of its descent, determined much about its character. Mountain rivers dropped quickly, losing elevation rapidly and gaining speed and erosive power. These steep rivers carved narrow valleys, transported large rocks, and created waterfalls where resistant layers of stone interrupted the descent. Lowland rivers, by contrast, had gentle gradients, dropping only inches per mile, and they flowed slowly, broad and meandering, carrying fine sediment and depositing it across wide floodplains. Ancient rivers followed the same physical laws, and their gradients changed over geological time as mountains rose and eroded, as continents shifted and tilted, as sea levels rose and fell. A river that began as a steep mountain torrent might, over millions of years, become a lazy lowland meander as the land around it wore down and flattened. Some ancient rivers disappeared entirely, not by drying up, but by being buried under layers of younger sediment. These buried river channels, preserved in the rock record, are called palaeochannels, and geologists find them by mapping changes in sediment type and structure. A palaeochannel might appear as a band of coarse sandstone cutting through finer mudstone, marking where a river once flowed across a floodplain. These buried rivers tell stories of ancient landscapes, revealing where water once ran, where forests once grew along the banks, where animals came to drink. In some cases, palaeochannels still hold water, flowing underground through permeable sandstone, becoming aquifers that modern humans tap for wells and irrigation. The ancient river continues its work, invisible but essential, moving water through stone just as it once moved water across the surface. The relationship between rivers and groundwater was always intimate. Rivers received water from underground springs, places where the water table intersected the land surface, and groundwater seeped or flowed into the channel. These springs provided base flow, the steady contribution of water that kept rivers running even during dry seasons when rain was absent. Ancient rivers depended on this groundwater connection, and their flow regimes reflected the geology beneath them. Rivers flowing over porous limestone might lose water, sinking into underground caverns and emerging miles downstream. Rivers flowing over impermeable clay might gain water continuously, fed by springs all along their length. This exchange between surface and subsurface was a hidden dimension of river life, a circulation that connected the visible flow with vast reservoirs of water stored in rock. Ancient rivers also shaped the evolution of plants in profound ways. The first plants to colonize land, over 400 million years ago, stayed close to water, their simple structures unable to transport moisture far from their roots. But rivers provided not just water, but also a means of dispersal. Spores and seeds fell into the current and traveled downstream, colonizing new habitats, spreading genetic diversity across landscapes. Some plants evolved specialized structures for water dispersal, seeds with waterproof coatings, fruits that floated, spores that could survive immersion. Rivers became highways for botanical expansion, connecting populations that would otherwise have been isolated, allowing plants to migrate in response to climate change, to recolonize areas after disturbance, to maintain genetic diversity across wide regions. The sediment load of ancient rivers was not evenly distributed throughout the year. During floods, rivers carried enormous quantities of material, sometimes increasing their sediment load by a factor of 100 or more. These flood pulses did most of the geological work, moving boulders that would sit immobile during normal flow, scouring channels down to bedrock, depositing thick layers of fresh sediment across floodplains. But during low flow periods, rivers carried almost nothing, and their beds became stable environments where organisms could settle and grow. This pulsing rhythm of transport and stability shaped the ecology of ancient rivers, creating a dynamic environment where only adaptable species could persist. Some organisms evolved life cycles synchronized with floods, reproducing rapidly during stable periods, surviving floods as resistant eggs or seeds, or by retreating to shelter backwaters. Ancient rivers interacted with ice in ways that seem strange from our modern perspective. During ice ages, glaciers advanced across continents, and rivers flowing from these ice sheets carried meltwater loaded with fine glacial flour, rock ground to powder by the moving ice. These glacial rivers were milky gray, their water so thick with suspended sediment that they appeared almost solid. The sediment load was so heavy that it settled out quickly when the river reached the sea, building deltas at an accelerated pace. Glacial rivers were also extremely cold, near freezing even in summer, and they supported specialized communities of cold-adapted organisms. When the ice retreated, these rivers changed character entirely, becoming warmer and clearer, and their ecosystems transformed as temperate species moved in to replace the cold specialists. Some ancient rivers flowed in directions that seem counterintuitive today. Rivers generally flow toward the sea, following the slope of the land, but the position of the sea changes over geological time, and so do the slopes. Ancient rivers sometimes flowed inland, toward interior basins that had no outlet to the ocean, creating vast lakes in the hearts of continents. The rivers that fed these lakes carried sediment and dissolved minerals, and because the water could only leave by evaporation, the lakes became salty over time, concentrating minerals until they formed thick deposits of salt, gypsum, and other evaporites. These ancient lake basins and the rivers that fed them are now preserved in the rock record, sometimes containing fossils of unique organisms that evolved in isolation, cut off from the ocean and from other river systems. The color of ancient river sediments tells us about the atmosphere they were deposited in. Red sediments, rich in iron oxide, formed in the presence of oxygen, indicating that the atmosphere contained free oxygen and that the climate was warm enough for iron to oxidize, to rust. Gray and green sediments, by contrast, formed in low oxygen or oxygen-free conditions, preserving iron in its reduced state. The transition from gray to red sediments in the rock record marks a fundamental change in Earth's atmosphere. The Great Oxidation event around 2.5 billion years ago, when photosynthetic organisms began producing oxygen in large quantities. Ancient rivers before this event flowed through a world without rust, carrying gray sediments rich in unoxidized iron. And the organisms that live in those rivers, if any, had to survive without the oxygen we consider essential. Ancient rivers carved caves, not just in limestone, but in any soluble rock. Water flowing underground, following fractures and bedding plains, slowly dissolved the rock and created passages, chambers, and intricate networks of tunnels. Some of these cave rivers still flow today, hidden beneath the surface, emerging only where the cave intersects the land surface. Ancient cave rivers are harder to recognize in the rock record, but geologists find evidence of them in unusual sediment patterns, in deposits of cave formations like stalactites and stalagmites, in fossils of cave-adapted organisms with reduced eyes and pale bodies. These underground rivers were complete ecosystems, supporting life in total darkness, fed by organic matter washed in from the surface. The power of ancient rivers to erode was not constant, but varied with the hardness of the rock they flowed over. Soft sedimentary rocks like shale and sandstone eroded quickly, allowing rivers to cut deep valleys in geologically short periods. Hard igneous rocks like granite resisted erosion, forcing rivers to flow around them or to cut narrow gorges over millions of years. This differential erosion created the very topography we see today, with some regions deeply dissected by river valleys and others standing as high plateaus or mesas. Ancient rivers were the sculptors of landscapes, but the rock itself determined the pace and pattern of that sculpture. Ancient rivers also transported heat, a fact easy to overlook but significant for regional climates. Water has a high heat capacity, meaning it can absorb and store large amounts of thermal energy without changing temperature dramatically. Rivers flowing from warm regions toward cooler ones carried heat with them, moderating temperatures along their banks. Rivers flowing from cold mountains into warm lowlands carried coolness, creating microclimates where temperature-sensitive organisms could survive outside their usual range. This thermal transport was especially important during periods of rapid climate change, when rivers acted as refugia corridors, allowing species to migrate along temperature gradients, following the conditions they were adapted to. The ancient rivers of Gondwana, the southern supercontinent that included what is now South America, Africa, Antarctica, Australia, and India, flowed through landscapes we can barely imagine. These rivers drained vast interior basins, crossed deserts and rainforests, and connected ecosystems that are now separated by oceans. When Gondwana began to break apart, around 180 million years ago, these rivers were disrupted, their courses severed by widening rifts that would become the Atlantic and Indian Oceans. But before the breakup, the rivers of Gondwana were among the longest and largest on Earth, and they supported unique assemblages of life, including early dinosaurs, ancient fish lineages, and plants that have no close modern relatives. Ancient rivers responded to volcanic eruptions in dramatic ways. Ash falling from the sky blanketed river catchments, clogging channels, smothering vegetation, and altering water chemistry. The ash was rich in minerals, and when it dissolved in river water, it released nutrients that could fertilize downstream ecosystems or, in high concentrations, poison them. Lahars, volcanic mudflows, raced down river valleys at high speed, carrying a slurry of ash, rock, and water that buried everything in their path. These catastrophic events were followed by periods of recovery, as rivers slowly cleared the ash, as vegetation regrew, as ecosystems reassembled. The rock record preserves layers of volcanic ash within river sediments, marking these moments of disruption and renewal. Some ancient rivers flowed through landscapes dominated by giant fungi during a period before trees evolved. In the Devonian, towering fungal structures called prototaxites reached heights of over 20 feet, and they grew along river banks and in floodplains, their spores dispersing in the water and air. These rivers moved through forests of fungus, a world that seems alien to us, where the dominant vertical structures were not plants but decomposers. The rivers carried spores and organic matter, connecting fungal populations, supporting early insects and other arthropods that fed on the fungi and on each other. The ancient rivers of the Carboniferous period, around 300 million years ago, flowed through swampy forests of giant ferns, horsetails, and club mosses. These plants grew to enormous sizes in the warm, humid climate, and when they died, They fell into the swamps and rivers, where low oxygen levels prevented complete decay. Over time, this accumulated plant material was buried and compressed, eventually forming the vast coal deposits that powered the Industrial Revolution. The rivers of the Carboniferous were agents of carbon burial, removing carbon dioxide from the atmosphere and locking it away in sediment, contributing to a global cooling that eventually led to an ice age. Ancient rivers also played a role in the phosphorus cycle, an element essential for life but often in short supply. Phosphorus does not have a gaseous phase, so it cannot cycle through the atmosphere like carbon or nitrogen. Instead, it moves through the landscape primarily via water, dissolved from rocks by weathering, carried by rivers to the sea, where it supports marine productivity. Ancient rivers were the main pathway for phosphorus from land to ocean, and changes in river flow, in erosion rates, in the chemistry of weathering, all affected the availability of this crucial nutrient. During periods of intense mountain building and erosion, rivers carried more phosphorus to the sea, potentially fueling blooms of marine life and affecting global oxygen levels. The braiding of ancient rivers, the splitting and rejoining of channels across a wide valley floor, created complex mosaics of habitat. Each braid was a separate channel, with its own flow velocity, depth, and sediment load, and the spaces between braids were gravel bars, islands, and wetlands. These braided rivers were dynamic, with channels shifting position during floods, cutting new paths, abandoning old ones. Organisms living in braided rivers had to be mobile, able to colonize new channels as they formed, able to survive the periodic scouring of floods. Braided rivers were common in glacial and periglacial environments, where sediment supply was high and vegetation was sparse, unable to stabilize the banks. Ancient rivers carried stories in their sediments, layered records of floods and droughts, of seasons and years, of climate shifts and tectonic events. Geologists read these stories by examining the grain size, the sorting, the sedimentary structures, the fossils, the chemical composition. A layer of coarse gravel records a flood. A layer of fine clay records a period of still water. Cross-bedding records the direction of current. Mud cracks record drying. Each layer is a page in the river's autobiography, and the entire sequence is a book that spans millions of years. The ancient rivers of Mars, now dry for billions of years, once flowed with liquid water across the Martian surface. These rivers carved valleys, transported sediment, and may have supported microbial life. The evidence for ancient Martian rivers comes from orbital images showing branching valley networks, from sedimentary rocks examined by rovers, from minerals that form only in the presence of water. These rivers flowed during a warmer, wetter period in Mars' early history, before the planet lost most of its atmosphere and surface water froze or evaporated. The story of Martian rivers is a story of planetary change, of a world that once had flowing water and may have been habitable, now cold and dry and silent. But here on Earth, ancient rivers continue to flow, not as the same water in the same channels, but as a continuity of process, a persistence of pattern. The rivers we see today are the descendants of rivers that flowed millions of years ago, following the same physical laws, responding to the same forces of gravity and erosion, connecting the same essential elements of the water cycle. When you stand beside a river, you are standing beside deep time, watching a process that has shaped the planet since water first condensed on the surface. Ancient rivers were patient. They did not rush to complete their work. A river might take 1,000,000 years to cut through a layer of resistant rock, but it would do so grain by grain, flood by flood, never stopping, never doubting. This patience is part of what makes rivers so calming to contemplate. They remind us that great changes happen slowly, that persistence is more powerful than force, that time is the most abundant resource in the universe. The meanders of ancient rivers grew more pronounced over time, as the river swung wider and wider, eroding the outside of each bend and depositing sediment on the inside. This lateral migration was a form of exploration, a way the river searched the landscape for the path of least resistance. Eventually, a meander loop might grow so exaggerated that the river cut across the narrow neck of land, separating the two sides of the loop, creating a shortcut and abandoning the old meander as an oxbow lake. This process repeated endlessly, and ancient floodplains were dotted with oxbow lakes in various stages of evolution. Some still connected to the river during floods, some completely isolated, some already filled with sediment and vegetation, becoming swamps and then dry land. Ancient rivers were also engineers of soil. The sediment they deposited on floodplains became the parent material for soil formation, and the annual floods replenished nutrients, preventing the soil from becoming exhausted. Civilizations that arose along ancient rivers benefited from this natural fertility, and they developed agriculture in these floodplains, growing crops without the need for fertilizers. The rivers were partners in this enterprise, predictable and generous, asking only that people respect the flood cycle and build their permanent settlements on higher ground. The sound of ancient rivers, that constant murmur of moving water, may have influenced the evolution of communication in early humans and their ancestors. Living near rivers, early hominins would have needed to communicate over the background noise of flowing water, perhaps favoring louder calls, perhaps developing more complex vocalizations that could be distinguished from the river's hum. This is speculation, but it reminds us that rivers were not just physical features of the landscape, but acoustic features, shaping the sensory environment in which life evolved. Ancient rivers carried pollen, the microscopic grains that plants produce for reproduction. Pollen is remarkably durable, and it preserves well in sediment, allowing scientists to reconstruct ancient plant communities by extracting and identifying pollen from river deposits. Each pollen grain has a distinctive shape and surface texture, and by counting the different types in a sediment sample, researchers can determine which plants were growing in the river's catchment at the time the sediment was deposited. This pollen record reveals changes in vegetation over time, showing how forests expanded and contracted, how grassland spread, how climate change affected plant communities. The ancient rivers of the Permian period, around 250 million years ago, witnessed the greatest mass extinction in Earth's history, an event that killed over 90% of marine species and 70% of terrestrial vertebrate species. The cause of this extinction is still debated, but massive volcanic eruptions in Siberia are the leading suspect, releasing enormous quantities of carbon dioxide and other gases, triggering rapid climate change. Rivers during this time carried the evidence of catastrophe: layers of ash, changes in sediment chemistry, a sudden disappearance of many fossil types, followed by a slow recovery as new species evolved to fill the empty niches. Ancient rivers also created natural dams, places where landslides, lava flows, or glacial ice blocked the channel and caused water to pool upstream. These natural dams were temporary on geological timescales, eventually breached by the rising water or eroded by seepage. And when they failed, they released catastrophic floods that reshaped the landscape downstream. The channeled scablands of Washington state were carved by such a flood, when an ice dam holding back glacial Lake Missoula failed repeatedly during the last ice age, releasing water in quantities that dwarf any modern river flood. The ancient rivers of tropical regions were and are hotspots of biodiversity. The warm, stable climate, the abundant rainfall, the complex structure of river and floodplain habitats all contribute to high species richness. The Amazon River Basin, for example, contains more fish species than any other river system on Earth, many of them found nowhere else. Ancient tropical rivers supported similarly diverse communities, and fossils from these environments reveal a profusion of life forms, from tiny invertebrates to large predators, all interconnected in complex food webs. Ancient rivers were also pathways for disease, carrying pathogens and parasites along with water and sediment. Organisms that caused waterborne illnesses evolved strategies to survive in rivers, to infect hosts that came to drink, to complete complex life cycles involving multiple host species. The relationship between rivers and disease is ancient, and it shaped the evolution of immune systems, the behavior of animals around water sources, and eventually, human efforts to treat and purify water. The flow of ancient rivers was not always downstream. Tides, where rivers met the sea, could push water upstream twice a day, creating a zone of brackish water where salt and fresh water mixed. This tidal zone was a unique habitat, fluctuating in salinity, in water level, in current direction, and it supported specialized organisms adapted to these changing conditions. Ancient tidal rivers left distinctive sediment patterns, with rhythmic layering that records the daily rise and fall of the tide, and these patterns allow geologists to reconstruct ancient tidal ranges and even the length of the day in the distant past, as tidal friction gradually slows Earth's rotation. Ancient rivers, in their quiet persistence, connected the highest mountains to the deepest oceans, the driest deserts to the wettest rainforests. They were the circulatory system of the continents, moving water, sediment, nutrients, organisms, genes, and information across the landscape. To understand rivers is to understand the planet, to see how everything is connected, how change in one place ripples outward, how the slow accumulation of small actions creates the grand patterns of geology and life. And so the ancient rivers flow through our imagination, through the rock record, through the landscapes we inhabit. They are always there, beneath the surface, in the shape of the valleys, in the fertility of the soil, in the fossils we find, in the water we drink. They remind us that we are part of a long story, that the processes shaping the earth today are the same processes that shaped it billions of years ago, that the water flowing past us now has flowed past countless other observers, other species, other worlds. There is comfort in this continuity, in this connection to deep time, in the knowledge that rivers will continue to flow long after we are gone, patient and persistent, carving the earth, carrying the world, quietly doing their work. The ancient rivers carried within them a kind of memory that went beyond sediment and stone. Every bend, every shift in current, every grain of sand settling on the bottom told a story not just of water moving downhill, but of the planet breathing, changing, reorganizing itself in the slowest possible dance. These rivers witnessed the rise and fall of mountain ranges that no longer exist, carried the dust of volcanoes that have long since eroded to nothing, and flowed through forests of plants that left no modern descendants. They were witnesses to almost everything, and they asked nothing in return but gravity and time. Some of the most ancient river deposits contain what scientists call palaeochannels, ancient soils that formed on floodplains millions of years ago. These buried soils preserve the chemistry of the atmosphere at the time, the types of plants that grew there, and even the activity of earthworms and roots. When you look at a cross-section of rock that was once a riverbank, you can see layers of soil stacked like pages in a book, each one representing a moment when the river paused, flooded gently, and allowed life to settle in before moving on. These palaeochannels are windows into vanished ecosystems, and they remind us that rivers were never just water. They were places where life took root again and again, across unimaginable stretches of time. Ancient rivers also played a quiet but essential role in the distribution of trace elements across the Earth's surface. Elements like selenium, molybdenum, and zinc, though needed only in tiny amounts by living organisms, were carried by rivers from eroding rocks to the oceans and floodplains where life could access them. Without this patient redistribution, many ecosystems would have been starved of the nutrients necessary for complex life. Rivers were the planet's circulatory system, not just for water, but for the very building blocks of biology. They carried these elements grain by grain, year by year, ensuring that life had what it needed, wherever it took hold. In some ancient river systems, scientists have found evidence of what are called incised meanders, where a river cut down into the landscape while maintaining its winding shape. This happens when the land is slowly uplifted by tectonic forces, and the river, rather than changing course, simply carves deeper into the rock. The result is a canyon that twists and turns like a river on a flat plain, a strange and beautiful merging of vertical and horizontal erosion. These incised meanders can be hundreds of meters deep, and they reveal the river's stubborn persistence. Even as the world rose beneath it, the river kept its path, cutting through stone rather than abandoning the course it had followed for ages. Rivers in the deep past also interacted with glaciers in ways that shaped entire continents. When glaciers advanced during ice ages, they blocked existing river valleys, forcing rivers to find new paths. When the glaciers retreated, they left behind enormous amounts of meltwater that carved new channels, some of which became the rivers we know today. The Great Lakes of North America, for example, were sculpted by glaciers, but the rivers that drained them were shaped by the chaotic floods that followed the ice's retreat. These glacial rivers carried unimaginable volumes of water, sediment, and ice, reshaping the landscape in mere centuries, a blink of an eye in geological terms, yet still slow enough that no single generation would have seen the full transformation. Ancient rivers also left behind what are called river terraces, flat benches of land that sit above the current river level. These terraces form when a river cuts down into its floodplain, abandoning the old level and creating a new, lower one. Over time, this process can repeat, leaving a staircase of terraces on either side of the river, each one representing a former floodplain. These terraces are often rich in archaeological and paleontological material because they were once the places where animals grazed, humans camped, and plants grew. Walking across a river terrace is like walking on a frozen moment in the river's history, a surface that once knew the rush of floodwaters but now sits quietly above, watching the river continue its work below. Some ancient rivers flowed in directions that seem strange to us now, because the continents have moved so much since then. Rivers that once flowed north might now be preserved in rocks that sit on a continent far to the south. The sediments they carried, the fossils they buried, and the minerals they deposited all moved with the tectonic plates, traveling thousands of kilometers over millions of years. This means that when we study ancient rivers, we are also studying the movement of the Earth's crust itself. The river is a thread that ties together not just landscapes, but entire chapters of planetary history, chapters that span oceans and continents and eons. Rivers in the Precambrian, the vast stretch of time before complex life appeared, were different in almost every way from the rivers we know. Without plants to hold the soil, without animals to burrow and aerate the ground, these rivers were more prone to sudden shifts and braiding. Their banks were bare rock and sand, and their floodplains were lifeless except perhaps for microbial mats. Yet even in this barren world, rivers were doing essential work. They were weathering rock, releasing nutrients, and creating the conditions that would eventually allow life to colonize the land. They were patient architects, building the foundation for a world they would never see, a world of forests and fields and cities, all made possible by the slow grinding of water over stone. Ancient rivers also carried what we might call chemical messages between different parts of the Earth system. When a volcano erupted far inland, the ash and gases it released would eventually be washed into rivers, which carried them to the sea. There, the nutrients in the ash could fertilize plankton blooms, which in turn affected the amount of oxygen in the atmosphere and the amount of carbon buried in ocean sediments. In this way, a single volcanic eruption could have effects that rippled through the climate system for thousands of years, all mediated by the patient flow of rivers. The river was a messenger, translating events on land into changes in the ocean and sky, connecting systems that might otherwise seem separate. Some of the most beautiful river deposits are found in what are called point bar sequences, where sediment accumulates on the inside bend of a meander. These deposits show a gradual change from coarse sediment at the bottom to fine sediment at the top, recording the river's energy as it shifted and slowed. Geologists can read these sequences like a story, seeing where the river was fast and where it was calm, where it flooded and where it retreated. Each layer is a sentence, each grain a word, and together they form a narrative of water and time that is both precise and poetic. The river wrote its own history, and we are only now learning to read it. Rivers in the ancient world also shaped the evolution of freshwater organisms in ways we are only beginning to understand. Freshwater fish, mollusks, and insects evolved in isolated river systems, each one developing unique adaptations to the specific chemistry, temperature, and flow of their home waters. When rivers merged or changed course, these isolated populations sometimes came into contact, leading to hybridization, competition, or cooperation. The result is a patchwork of biodiversity that reflects not just the biology of the organisms, but the history of the rivers themselves. Every species of freshwater mussel, every endemic fish, carries within its genes a map of ancient river connections and separations, a living archive of hydrological history. Ancient rivers also played a role in the formation of certain types of gemstones and precious minerals. Diamonds, for example, are brought to the surface by volcanic eruptions, but they are often transported and concentrated by rivers. The same is true for gold, sapphires, and many other valuable minerals. Rivers sort these materials by weight and size, concentrating them in places where the current slows, such as behind boulders or in deep pools. These placer deposits have been mined by humans for thousands of years, but they were created by rivers over millions of years, patiently gathering and sorting the treasures hidden in the Earth's crust. The river, in its slow and steady way, was a miner long before we were. Some ancient rivers left behind trace fossils, not of the organisms themselves, but of their activities. Burrows, tracks, and feeding marks preserved in river sediments tell us about the behavior of creatures that lived along the banks and in the shallows. These trace fossils are often more informative than body fossils because they show us how animals moved, fed, and interacted with their environment. A line of footprints crossing a sandbar tells a story of migration or hunting. A burrow in the mud tells of a creature seeking shelter from the current or from predators. These traces are the river's way of remembering not just what lived, but how it lived, and they add depth and texture to our understanding of ancient ecosystems. Rivers in deep time also influence the distribution of isotopes, the different forms of elements that have the same number of protons but different numbers of neutrons. By measuring the ratios of isotopes in river sediments, scientists can reconstruct ancient temperatures, rainfall patterns, and even the types of plants that grew in the watershed. For example, the ratio of oxygen isotopes in shell fragments can tell us whether the river was fed by glacial meltwater or tropical rainfall. The ratio of carbon isotopes can reveal whether the surrounding landscape was dominated by forests or grasslands. These isotopic signatures are like fingerprints, unique to each river and each moment in time, and they allow us to see the ancient world with a clarity that would otherwise be impossible. Ancient rivers also created what are called sedimentary fans, cone-shaped deposits that form where a river exits a mountain range and spreads out onto a plain. These fans are built up over millions of years, layer by layer, as the river carries sediment from the highlands and deposits it at the mountain front. The result is a gently sloping surface that can be tens or even hundreds of kilometers across. Sedimentary fans are important because they preserve a record of the mountain's erosion, showing how the landscape changed over time as the peaks wore down and the valleys deepened. They are also important for human societies because they often contain aquifers, underground layers of water-saturated sediment that provide drinking water for millions of people. Some ancient rivers flowed through landscapes that were so flat and featureless that they barely had a defined channel. These rivers, called anastomosing rivers, split into multiple small channels that braided and rejoined across a wide floodplain. The water moved slowly, and the channels shifted frequently, creating a complex mosaic of wetlands, ponds, and low ridges. These rivers were common in the past, especially in areas with high water tables and low gradients, and they supported rich ecosystems of fish, amphibians, and waterbirds. The sediments they left behind are often organic rich and finely layered, recording subtle changes in water level and vegetation over time. They remind us that not all rivers are fast and dramatic. Some are slow and quiet, spreading across the land like a gentle hand. Rivers in the ancient world also transported heat in ways that affected local and regional climates. A river fed by cold mountain snowmelt could lower the temperature of the air above it, creating a cool corridor through an otherwise hot landscape. Conversely, a river warmed by geothermal springs or by flowing through sun-baked deserts could raise the temperature of the areas it passed through. This thermal transport was especially important in the past, when the arrangement of continents and the patterns of ocean currents were different from today. Rivers helped to smooth out temperature extremes, making the land more hospitable for life, and their thermal influence extended far beyond their banks, affecting weather patterns and vegetation zones across entire regions. Ancient rivers also left behind what geologists call cut-infill sequences, where a river eroded a channel and then later filled it in with new sediment. These sequences can be confusing to interpret because they represent two different events, erosion and deposition, happening in the same place at different times. But they are also valuable because they show us how rivers respond to changes in climate, sea level, or tectonic activity. A period of erosion might indicate a drop in sea level or an increase in rainfall, while a period of deposition might indicate the opposite. By studying these sequences, scientists can reconstruct the environmental history of a region, seeing how the river adapted to changing conditions over thousands or millions of years. Some ancient rivers carried so much dissolved calcium carbonate that they deposited it along their banks and beds, forming a rock called tufa. Tufa forms in cool, clear waters where the river flows over limestone or other carbonate rocks, dissolving them and then precipitating the calcium carbonate in a new location. The result is a porous, spongy rock that often preserves delicate structures like moss, leaves, and even insect wings. Tufa deposits are beautiful and fragile, and they tell us about the chemistry of ancient rivers, the plants that grew along their banks, and the conditions that allowed these minerals to form. They are a reminder that rivers are not just movers of sediment, but also creators of stone, building new landscapes even as they erode old ones. Rivers in the deep past also played a role in the nitrogen cycle, the movement of nitrogen between the atmosphere, the land, and the oceans. Nitrogen is essential for life, but most organisms cannot use the nitrogen gas that makes up most of the atmosphere. It must first be converted into a usable form by certain bacteria, a process called nitrogen fixation. Rivers carried these bacteria, along with the nitrogen compounds they produced, from the land to the sea, where they fertilized marine ecosystems. In this way, rivers were conduits for one of the most important nutrients on Earth, connecting terrestrial and aquatic systems and ensuring that life had the nitrogen it needed to build proteins, DNA, and other essential molecules. Ancient rivers also created what are called levees, natural ridges that form along the banks of a river when it floods. During a flood, the river carries a heavy load of sediment, but as the water spills over the banks and slows down, the coarsest sediment is deposited first, right at the edge of the channel. Over many floods, this sediment builds up into a low ridge that can be several meters high. Levees are important because they help to contain the river, preventing it from spreading too widely across the floodplain. They also create a distinctive topography, with the river flowing on top of a ridge and the surrounding land sloping gently away. This topography has influenced where humans have built their homes and farms for thousands of years, because the levees are higher and drier than the floodplain, offering some protection from floods. Some ancient rivers flowed through landscapes that were rich in iron, and as the iron-bearing minerals weathered and dissolved, they gave the river a reddish or orange color. When this iron-rich water reached the ocean or a lake, the iron precipitated out, forming layers of iron-rich sediment that eventually became iron ore. These deposits, called banded iron formations, are some of the most important sources of iron for modern industry, but they also tell a story about the ancient Earth. Most banded iron formations were deposited more than 2 billion years ago, at a time when the atmosphere had very little oxygen. The iron could remain dissolved in the water because there was no oxygen to react with it. But when photosynthetic organisms began producing oxygen, the iron precipitated out, creating these distinctive layered rocks. Rivers were the conduits for this iron, carrying it from the land to the sea, where it recorded one of the most important transitions in Earth's history, the rise of oxygen. Rivers in the ancient world also influenced the distribution of diseases and parasites. Many parasites have complex life cycles that involve both aquatic and terrestrial hosts, and rivers provide the pathways that allow these parasites to spread. For example, certain flatworms spend part of their life cycle in freshwater snails and part in mammals or birds that drink from the river. By connecting different habitats and different species, rivers created opportunities for parasites to evolve and diversify. This might seem like a negative thing, but parasites are an important part of ecosystems, regulating host populations and driving evolutionary adaptations. Rivers were not just conduits for water and sediment, but also for the complex web of interactions that make up a healthy ecosystem. Ancient rivers also left behind what are called palaeochannels, the buried remains of old river channels that are no longer active. These palaeochannels can be detected using ground-penetrating radar, satellite imagery, or simply by digging down through the layers of sediment. They are important for several reasons. First, they show us where rivers used to flow, which can help us understand how the landscape has changed over time. Second, They often contain water, making them valuable sources of groundwater in arid regions. Third, they can contain archaeological material, because humans often settled along rivers, and when the river moved, it buried the evidence of their presence. Palaeochannels are like hidden highways beneath the surface, still carrying water and still telling stories, even though the river itself has moved on. Some ancient rivers flowed through landscapes that were so rich in organic matter that the river itself became acidic. This happens in areas with extensive peat bogs or dense forests, where decaying plant material releases organic acids into the water. These acidic rivers, sometimes called blackwater rivers, have a distinctive dark color and a low pH. They are poor in nutrients and support different types of organisms than neutral or alkaline rivers. The acidity also affects the types of minerals that can dissolve and be transported, leading to different patterns of erosion and deposition. Ancient blackwater rivers left behind sediments that are often dark and organic rich, and they tell us about the types of vegetation that grew in the watershed and the climate conditions that allowed such dense plant growth. Rivers in deep time also played a role in the sulfur cycle, the movement of sulfur between rocks, water, and the atmosphere. Sulfur is released when certain minerals, especially pyrite, weather and dissolve. Rivers carried this dissolved sulfur to the ocean, where it was used by marine organisms or precipitated as sulfate minerals. In some cases, the sulfur was converted to hydrogen sulfide, a toxic gas that can accumulate in stagnant waters and kill fish and other organisms. By transporting sulfur, rivers influenced the chemistry of the oceans and the atmosphere, and they played a role in regulating the Earth's climate and the health of marine ecosystems. The sulfur cycle is less well known than the carbon or nitrogen cycles, but it is equally important, and rivers have been key players in it for billions of years. Ancient rivers also created what are called scroll bars, curved ridges that form on the inside of a meander as the river migrates across the floodplain. These scroll bars are the result of sediment being deposited as the river shifts its position, and they create a distinctive pattern of parallel ridges and swales that can be seen from the air. Each ridge represents a former position of the riverbank, and together they record the river's movement over time. Scroll bars are often covered with vegetation, and the swales between them can hold water, creating a habitat for wetland plants and animals. They are a beautiful example of how rivers shape the land, not just by eroding it, but by building it up, creating new landforms and new habitats as they go. Some ancient rivers carried so much sediment that they built up their beds faster than they could erode them, causing the river to rise above the surrounding landscape. These elevated rivers, called perched rivers, are unstable and prone to avulsion, suddenly breaking out of their channel and finding a new path to the sea. When this happens, the old channel is abandoned and slowly fills in with sediment, while the new channel begins the process of building itself up again. Perched rivers were common in the past, especially in areas with high sediment loads and low gradients, and they created complex landscapes of abandoned channels, wetlands, and levees. They remind us that rivers are not permanent features of the landscape, but dynamic systems that are constantly changing and adapting. Rivers in the ancient world also influenced the evolution of plants in ways that are still being discovered. Some plants evolved to disperse their seeds by water, producing seeds that could float and remain viable for weeks or months. These seeds would be carried downstream by the river, colonizing new areas and spreading the plant's range. Other plants evolved to tolerate flooding, developing roots that could survive being submerged for long periods or stems that could bend without breaking in the current. Still others evolved to take advantage of the nutrients deposited by floods, growing quickly and producing large amounts of seeds before the next flood arrived. The river shaped the plants, and the plants shaped the river, creating a feedback loop that has been running for hundreds of millions of years. Ancient rivers also left behind what are called clay plugs, layers of fine sediment that fill in abandoned channels and oxbow lakes. These clay plugs are important because they seal off the old channel, preventing water from flowing through it and allowing it to become a distinct feature of the landscape. Over time, the clay plug can become compacted and cemented, turning into a solid barrier that is resistant to erosion. These plugs preserve the shape of the old channel and the sediments within it, creating a kind of time capsule that can be opened by geologists thousands or millions of years later. They are a reminder that rivers not only create and destroy, but also preserve, locking away pieces of the past for future discovery. Some ancient rivers flowed through regions that were rich in volcanic activity, and the interaction between the river and the lava created unique landscapes. When lava flows into a river, the water can cool the lava so quickly that it shatters into fragments, creating a rock called hyaloclastite. Conversely, the heat from the lava can boil the river water, creating steam explosions that throw fragments of rock and lava high into the air. These interactions are violent and dramatic, but they are also creative, producing new landforms and new types of rock. The river and the volcano are opposites in many ways, one cool and flowing, the other hot and solid. But when they meet, they create something entirely new. Rivers in deep time also transported what scientists call cosmogenic nuclides, rare isotopes that are created when cosmic rays strike rocks on the Earth's surface. By measuring the concentration of these isotopes in river sediments, scientists can estimate how long the sediment has been exposed to cosmic rays, which in turn tells them how quickly the landscape is eroding. This technique, called cosmogenic nuclide dating, has revolutionized our understanding of erosion rates and landscape evolution. It shows that rivers erode the land at rates that vary widely depending on climate, rock type, and tectonic activity, but that are always slow by human standards, measured in millimeters per century or meters per million years. The river is patient, and the landscape yields to it, grain by grain, year by year. Ancient rivers also created what are called floodplain forests, dense woodlands that grew on the nutrient-rich soils deposited by floods. These forests were different from upland forests, with different species of trees and different structures. They were adapted to periodic flooding, with trees that could tolerate having their roots submerged for weeks at a time. The forests, in turn, influenced the river, slowing the water during floods, trapping sediment, and providing habitat for countless organisms. The relationship between the river and the forest was symbiotic, each one supporting and shaping the other. These floodplain forests were among the most productive ecosystems on Earth, and they played a crucial role in the carbon cycle, storing carbon in wood and soil and releasing oxygen into the atmosphere. Some ancient rivers left behind what are called armored beds, where the surface of the riverbed is covered with large stones that protect the finer sediment beneath from erosion. This happens when a river has enough energy to move the small and medium-sized sediment, but not enough to move the largest stones. Over time, the smaller sediment is washed away, leaving only the large stones on the surface. These armored beds are stable and resistant to erosion, and they can persist for thousands of years. They are also important habitats for fish and invertebrates, providing shelter from the current and from predators. The river, by sorting its sediment, creates its own protection, building a shield that allows it to flow without tearing itself apart. Rivers in the ancient world also played a role in the phosphorus cycle, the movement of phosphorus between rocks, soil, water, and living organisms. Phosphorus is essential for life, used in DNA, cell membranes, and energy transfer, but is often in short supply because it does not have a gaseous phase and is easily locked up in minerals. Rivers were the main way that phosphorus moved from the land to the sea, weathering phosphorus-rich rocks and carrying the dissolved phosphorus downstream. In the ocean, this phosphorus fertilized plankton blooms, which in turn supported fish, whales, and seabirds. Without rivers, the phosphorus would remain locked in the rocks, and life in the oceans would be much less abundant. The river was a liberator, freeing the phosphorus and allowing it to cycle through the living world. Ancient rivers also left behind what are called varves, thin layers of sediment that represent a single year of deposition. Varves form in lakes or slow-moving rivers where there is a strong seasonal cycle. In the spring and summer, when the river is carrying a lot of sediment, a thick, coarse layer is deposited. In the fall and winter, when the flow slows down, a thin, fine layer is deposited. By counting the varves, scientists can determine the age of the sediment with great precision, sometimes to the exact year. Varves are like tree rings, each one a record of a single year. and together they form a continuous archive of climate and environmental change that can stretch back tens of thousands of years. The river, by responding to the seasons, created its own calendar. Some ancient rivers flowed through landscapes that were so rich in salt that the river itself became salty. These saline rivers are rare today, but they were more common in the past, especially in arid regions where evaporation exceeded rainfall. The salt came from the weathering of salt-rich rocks or from the evaporation of ancient seas that had once covered the land. Saline rivers supported different types of organisms than freshwater rivers, including brine shrimp, salt-tolerant fish, and specialized bacteria. The sediments they left behind are often rich in evaporite minerals like halite and gypsum, which form when the salty water evaporates. These deposits tell us about the climate and the hydrology of the ancient landscape, showing us where deserts existed and where inland seas once spread. Rivers in deep time also influence the distribution of heat within the Earth's crust. When a river cuts down into the landscape, it removes rock and exposes deeper, warmer layers. This can increase the flow of heat from the Earth's interior to the surface, affecting geothermal gradients and the temperature of groundwater. In some cases, rivers have cut so deeply that they have exposed rocks that were once several kilometers below the surface, rocks that have been heated and deformed by the pressure and temperature of the deep crust. These exposed rocks tell us about the deep structure of the continents and the forces that have shaped them, and they remind us that rivers are not just surface features, but agents that connect the surface to the deep interior of the planet. Ancient rivers also created what are called slack-water deposits, layers of fine sediment that are deposited in sheltered areas during floods. These deposits form in places where the floodwater slows down, such as behind boulders, in caves, or in side channels. Because they are protected from the main current, slack-water deposits can preserve delicate structures like ripple marks, mud cracks, and even raindrop impressions. They also preserve a detailed record of flood history, with each layer representing a single flood event. By studying slack-water deposits, scientists can reconstruct the frequency and magnitude of past floods, information that is crucial for understanding flood risk and for managing rivers in the present. The river, even in its most violent moments, leaves behind clues that help us understand its behavior. Some ancient rivers carried so much dissolved silica that they deposited it as a rock called chert. Chert is a hard, fine-grained rock that forms when silica precipitates out of water, often in the form of tiny crystals or amorphous silica gel. It is common in ancient river and lake deposits, especially in areas where the water was warm and rich in silica from weathering volcanic rocks. Chert is important because it is very resistant to weathering and erosion, so it preserves structures and fossils that would otherwise be destroyed. It is also important to human history because it was one of the main materials used for making stone tools. The river, by concentrating and depositing silica, provided early humans with one of the resources they needed to survive and thrive. Rivers in the ancient world also played a role in the distribution of microplastics, though of course this is a very recent phenomenon in geological terms. But the principle is the same as it has always been. Rivers carry whatever is in their watershed, whether it is sediment, nutrients, or pollutants, and transport downstream. In the past, rivers carried natural materials, but they did so with the same patient efficiency that they carry everything else. They sorted, transported, and deposited, creating patterns that reflected the energy of the water and the properties of the material. Understanding how ancient rivers worked helps us understand how modern rivers work and how they will respond to the changes we are imposing on them. Ancient rivers also left behind what are called palaeocurrent indicators, features in the rock that show which way the river was flowing when the sediment was deposited. These indicators include cross-bedding, ripple marks, and the orientation of elongated pebbles. By measuring these features, geologists can reconstruct the direction of ancient rivers, even when the river itself has long since vanished. This information is valuable for understanding the geography of the past, for finding resources like oil and gas that are often associated with ancient river deposits, and for reconstructing the tectonic history of a region. The river, by shaping the sediment, left behind a compass that points to the past. Some ancient rivers flowed through landscapes that were so rich in organic matter that the river itself became a source of methane, a potent greenhouse gas. This happens when organic matter is buried in oxygen-poor sediments, and is decomposed by bacteria that produce methane as a byproduct. The methane can bubble up through the water or be transported downstream, where it is released into the atmosphere. In the ancient world, before humans began burning fossil fuels, rivers were one of the natural sources of methane, and they played a role in regulating the Earth's climate. The amount of methane produced by rivers varied depending on the amount of organic matter in the watershed, the temperature of the water, and the oxygen levels in the sediment, but it was always part of the complex web of interactions that make up the Earth system. Rivers in deep time also created what are called nick points, abrupt changes in the slope of the riverbed that often mark the boundary between different rock types or the location of a fault. Nick points are places where the river is actively eroding, cutting down through resistant rock to reach the softer rock below. They migrate upstream over time, as the river erodes the rock at the base of the nick point and causes the rock above to collapse. Nick points are important because they show us where the river is adjusting to changes in base level, tectonic uplift, or climate. They are also beautiful, often forming waterfalls or rapids that are among the most dramatic features of a river. The river, in its patient way, is always seeking equilibrium, and the nick point is a sign that has not yet found it. Ancient rivers also influence the distribution of rare earth elements, a group of metals that are essential for modern technology but are found in only a few places on Earth. These elements are released when certain minerals weather, and they are transported by rivers to the ocean or to lakes, where they can be concentrated in sediments. In some cases, ancient river deposits are rich enough in rare earth elements to be mined, providing a crucial resource for industries that depend on them. The river, by weathering and transporting these elements, created deposits that we are only now learning to find and use. It is a reminder that the work rivers did millions of years ago is still benefiting us today. Some ancient rivers left behind what are called mud drapes, thin layers of fine sediment that cover coarser sediment like a blanket. Mud drapes form when a river floods and then the floodwater recedes, leaving behind a layer of suspended mud that settles out of the still water. These drapes are important because they preserve the surface of the underlying sediment, including features like ripple marks and animal tracks. They also create a layered structure in the rock that can be used to interpret the river's behavior. Each mud drape represents a single flood event, and together they form a record of the river's rhythm, its cycles of high and low water, its response to storms and seasons. Rivers in the ancient world also played a role in the distribution of heat-loving bacteria, organisms that thrive in hot springs and geothermal areas. When a river flows near or through a geothermal area, it can carry these bacteria downstream, spreading them to new locations. Some of these bacteria are capable of surviving in extreme conditions, including high temperatures, acidic water, and low oxygen levels. They are among the oldest forms of life on Earth, and they may have been among the first organisms to colonize the land, using rivers as highways to spread from one hot spring to another. The river, by connecting these isolated oases of heat, allowed life to persist and diversify in environments that would otherwise be too harsh. Ancient rivers also created what are called sediment waves, large-scale ripples that form on the riverbed when the current is strong and steady. These waves can be several meters high and tens of meters long, and they migrate slowly downstream as sediment is eroded from the upstream side and deposited on the downstream side. Sediment waves are a sign that the river is transporting a large amount of sediment, and they are often found in rivers that are fed by glaciers or that drain steep, eroding mountains. When these waves are preserved in the rock record, they tell us about the energy of the ancient river and the amount of sediment it was carrying. They are a frozen moment of motion, a snapshot of the river in full flow. Some ancient rivers flowed through landscapes that were so rich in limestone that the river itself became a sculptor, carving caves and tunnels through the rock. This happens when the river flows underground, dissolving the limestone and creating passages that can be kilometers long. Over time, these passages can grow into vast cave systems, with underground rivers, waterfalls, and lakes. When the water table drops or the river finds a new path, these caves can be left dry, filled with beautiful formations like stalactites and stalagmites. The river, by dissolving the rock, created a hidden world beneath the surface, a world that is still being explored and mapped today. Rivers in deep time also influenced the distribution of hydrogen, the most abundant element in the universe. Hydrogen is released when water reacts with certain minerals, especially those that contain iron. This process, called serpentinization, occurs when water seeps into cracks in the Earth's crust and reacts with iron-rich rocks, producing hydrogen gas and heat. Rivers can carry this hydrogen-rich water to the surface, where it can be used by certain bacteria as a source of energy. These bacteria, called hydrogenotrophs, are thought to be among the most ancient forms of life, and they may have thrived in the early Earth when hydrogen was more abundant. The river, by transporting hydrogen, supported these ancient ecosystems and played a role in the origin and evolution of life. And so the ancient rivers flow on, through the layers of time and stone, through the cycles of climate and life, through the rise and fall of mountains and seas. They are patient, persistent, and powerful, shaping the world grain by grain, year by year, eon by eon. They ask nothing of us but our attention, and in return they offer us a glimpse into the deep history of the planet, a history written in sediment and stone, in fossils and minerals, in the curves of a meander and the layers of a delta. They remind us that the Earth is old, that change is slow, and that everything is connected. They invite us to slow down, to breathe, to rest, and to remember that we too are part of this ancient story, this long and patient unfolding of water and time.